Alright, so you may have noticed I sort of did an atrocity in how I formatted this. The first part of this question is here, and then it feeds from here all the way up here. And the reason I did this was to fit this all at the top, and because this is a really long problem, I typically don't, well, it's fairly long. I typically don't do problems that are this long, but I'm doing this one because this is a really important problem, because this talks about, I don't know if this is technically the same thing, but it's basically localization. And this is, we could have basically done the entire chapter of creating fields. We could have done it like this, I'm pretty sure. I'm pretty sure this is just a generalization. So anyways, let's get to it. So for equivalence, so first we have to do, this is an equivalence relation. AS is equivalent to AS because for all S, for all U and S, U AS minus AS equals U times 0 equals 0. So in particular, there is some U in S which satisfies this, and so that's what it means for these to be equivalent. For symmetry, AS is equivalent to BT if and only if there is some U in S such that U of AT minus BS equals 0 if and only if. As you can see, this stuff for checking equivalence is not super exciting. But this is 0. As the minus, you just bring the minus out. This is if and only if BT AS. So here if A, so here if A1 S1 is equivalent to A2 S2 by U2, and by that I mean that U2 is this is the value of, is the element of S such that U2 times A1 S2 minus A2 S1 equals 0, and A2 S2 is equivalent to A3 S3 by U3, then certainly U1 U2 S2 is an element of S because U1 and U2 and S are all in S, and this is a S is a submonoid, so it's closed under multiplication. And what happens when we do U1 U2 S2 and we multiply it by A1 S3 minus A3 S1? We want this to be 0. Anyways, U1, U2, you basically just do a bunch of calculations. 1S3 minus 3S1. And then we're going to do an analysis trick, which is where you subtract and add something useful. I guess it's not just an analysis trick, but it comes up a lot in analysis, especially in doing the triangle inequalities. A2S1. Anyway, so we get U1S1 times U2 A2S3 minus A3S2. But now look, this thing is 0 because U1 is defined as such, and similarly U2 is 0, so this is 0. So A1 S1 is equivalent to A3 S3. And so tilde is an equivalence relation. So that finishes that. So next, to prove RS inverse is a ring, start with plus. Let's see here. A over S plus B over T equals AT plus BS over ST, and AT plus BS is in R because R is a ring, and ST is in S because S is a multiplicative monoid. So A over S plus B over T is in RS inverse. So there we go. For associativity, and yes, we do have to check associativity. I wonder, we could probably just be like, hey, look at the text and see how they did this part. Actually, no, I looked back and the text tells you as the reader to verify this. Probably because, as you can see, it's really tedious. STU. Okay, so now we're scrolling down. And this is equal to ATU plus BSU plus CST. Just basically expand everything out for STU. And then what we can do is this. STU. That's just A over S plus what becomes B over T plus C over U. So there we go. For 0, A over S plus 0 over 1 equals A times 1 plus 0 times S over S times 1, which is A over S, which is also 0 times S plus A times 1 over 1 times S, which is 0 over 1 plus A over S. So we have a 0 element given by 0 over 1. Okay? See here. Also, well, I guess, do we have to worry about no, you don't really have to worry about equivalence classes. Or maybe you do. If you have to worry about equivalence classes at all, work it out yourself. I'm not going to go into that much. I'm already going into a lot of detail as it is. But it all works out. So also we want to do inverses. A over S plus negative A over S equals AS minus AS over S squared, which is equal to 0 over S squared, which is equivalent to 0 over 1, which is, of course, equivalent to 0 over S squared, which is equal to, oh no, and I'll just say negative A over S plus A over S is equivalent to 0 over 1. Also, so that takes care of inverses, and certainly negative A over S is in R S inverse because R is a ring, so it has additive inverses given by negative A. So also commutativity is pretty obvious. I'll write it out anyways. AT plus BS over ST. Then this is just, we use additivity, commutativity on top, and multiplicative commutativity on the bottom, and we get this, which becomes this. So hence, RS inverse plus 0 is an abelian group. All right, so next we move on to multiplication. A over S times B over T equals AB over ST, which is in RS inverse. We have A over S times B over T times C over U is AB over ST times CU, which is ABC over STU. I'm not even going to use parentheses because we know R and S to be associative, or yeah, R is associative. But anyways, just do this for U. 1 over 1 times A over S equals A over S equals A over S times 1 over 1. So hence, that's all we need, because all we need is that it's a multiplicative monoid, because all you need is you need closure, you need associativity, and you need an identity element. So lastly, we need distributivity. Cu is A over S times Bu plus Ct over Tu equals ABU plus ACT over STU. Now here we actually use a neat trick. By neat, I mean it's not really neat, it's just boring, because this is boring. You multiply it by 1, but 1 we know is equivalent to S over S, because you just check the equivalence relation thing, and it works. And this is ABSU plus ACST over STSU, because you bring the S over and then you just move things around a little bit using commutativity. This is AB for ST plus AC over SU. I'm just going to write as A over S times B over T, A over S times C over U. And then there is another distributivity thing that you should check usually, which is you have B plus T plus C times B over T plus C over U, but the A over S is over here. But we don't have to check that because we know that this is a we have commutativity of multiplication. Right. Well, wait a minute. We have, is R commutative? R is commutative. Yeah. Yeah. So that's all fine. So we have commutativity. And so the other distributivity, the other distributive law follows from the fact that this is a commutative ring. So there we go. So hence, our S inverse is a ring. Now we're done with this problem. Just kidding. Now what do we want? We want zero divisors, something about them. I'm just going to start proving it, and then I don't want to scroll back up and cause my computer to catch on fire, so I'm just going to go by my notes. Suppose no element of S is a zero divisor. Now let A be an element of R such that phi of A is phi of A is A over 1, which is, suppose it's equivalent to 0 over 1. Then there exists some S and S such that, what does this mean by definition? AS equals 0. If A is non-zero, then S is a zero divisor, which is impossible. Thus, A equals 0, so kernel of phi. So, if no element of S is a zero divisor, and if phi of A is maps to the zero element, then A must be zero, and so the kernel of phi consists entirely of the element 0. So phi is injective. Conversely, suppose phi is injective, then for all A in R set minus 0, phi of A, which is A over 1, is not equivalent to 0, 1. Oh, phi of A, by the way, sends A to A over 1, and it's a nice map. This is not equivalent to 0 over 1, which means there is no S in S such that psi equals 0, so S contains no zero divisors. So hence we have proved that S contains no zero divisors if and only if this map phi is injective. And so now we're done. Nope, we're not. Finally, if S is in S, then S over 1 times 1 over S. 1 over S is certainly an element of our S inverse. This is S over S, and we know this is equivalent to 1 over 1. And similarly, 1 over S times S over 1 is equivalent to 1 over 1. So S over 1 inverse is precisely 1 over S, which is an element of our S inverse. And hence, the units, see here, and so the collection of points S over 1 are units. And that, let me just verify that this is precisely what we wanted to show at the end here. Show that the elements S over 1 are units. Right. We don't know that these are all the units per se, but we know that in particular, these are units. So there we go. And you can kind of see if you want to do the analog of this with, like, say, with regular, like, rational numbers, then you would take, like, R to be the integers, and you could take S to be non-zero natural numbers, and then you could put the equivalence relation, and I'm pretty sure, non-zero integers, I meant. No, strictly positive integers. Yeah. R is, because when you have fractions, R is Z, and S is natural numbers, or non-zero positive integers. And yeah, of course, certainly all the things, anything that's a non-zero integer, you divide it by 1, it's invertible, and you just do 1 over the thing, and that's the inverse, and so those end up being units. But of course, in the rationals, every non-zero element is invertible, and so there are more units than just that. But yeah, so the nice thing about this is you can kind of build fractions, not just out of, like, the way you would build the rationals. You could just take any ring and any whatever S needs to be, and you can construct fractions, basically. And so there you go. This completes this problem.